This is a look at some of the devices currently on the market for both bugging rooms and tapping telephones. As you can see by our selection, there are quite a few units available, and they vary greatly in their looks and their capacities. These are infinity transmitters. Although they go on the telephone, they're actually room bugs, allowing one to hear what's going on in the room from another telephone. This is an old-fashioned style that doesn't work on the new telephones. This one is a dedicated infinity transmitter. When you call up, the phone never rings, but rather transmits the sound. It needs a dedicated line all by itself. A number of other units on the market are set up so the telephone will ring one or more times, allowing the user a window of vulnerability in which to grab the line and listen to the room conversation. This little unit here goes in the telephone and does exactly this. It's also possible now to buy complete phones with infinity transmitters built in. This one from Listen Electronics, you dial, it rings once, and you have 12 seconds in which to dial back, and it will grab the line and let you hear room conversation. Very difficult units to find. These are telephone taps. They're designed to pick up and rebroadcast telephone conversations. Some of them have batteries for longer range but shorter life, but most of them attach directly across the telephone wire itself. This means they can stay active forever. This is a 3-wire bug. It gets room conversation as well as telephone conversation and rebroadcasts it. This is a modern 3-wire bug, does approximately the same thing. This teeny little unit is often hidden in the handset of the telephone itself. Very powerful little unit. This is a law enforcement model, works well too. These are room bugs. Most of them are powered by batteries, either externally or internally. They can be hidden any place in a room. They're very sensitive. They'll pick up conversation from quite a few feet away. This is simply a professional wireless mic. It's been left in the on position and can be placed anywhere in the room. This is a very powerful little unit. Fully adjustable frequency built-in microphone. These two devices run off the AC power. This one clamps across an AC cord. This obviously is designed to go right inside a wall socket. It has a transmitter built directly into the back of it. It will operate continuously as long as it's left in place and there's power in the house. These are examples of what we're looking for. Notice these units, notice how small they are. We need to find them. These are telephone dropout recorders. They're designed to pick up the telephone conversation when the phone is lifted off the hook and start a tape recorder. Some modern recorders do this automatically, while others require the addition of these small units. They're attached directly to the telephone lines and don't hinder the conversation in any way. This is a miniature video camera and fiber optics. This combination, although it doesn't use any wire, can transmit video and sometimes audio several thousand feet. These devices are often hidden in false ceilings. They're also commercially available in clocks, smoke detectors, phony safes, and books. The two things we're going to look at now are bugs and taps. Now there's a difference. When I say bugs, I'm referring to something that reproduces room audio. Phones can be bugged. This phone can be rigged so it reproduces the room audio either down the wire or through the air to a monitor of some sort. Normally, bugs are in other environments. Taps reproduce phone conversation. That's all. A tap, strictly speaking, will not reproduce the conversation going on in the room. A bug will. Some devices are designed to do both. They'll pick up phone conversation and room conversation. These are known as three-wire bugs. They're usually in the phone or on the phone wire. What we're going to look at first is bugs, what you do about them. First thing you do is you assess your threat level. In other words, sit down and plan it out. Who wants you? Jealous spouse, you're suspicious of a business partner, something like that. That's one level of threat, and that level of threat we can cope with pretty well by following a few fairly simple things. We can eliminate that level of threat. On the other hand, if you think the DEA wants you, the FBI, somebody even higher up than that, you got problems. They're going to use real good stuff that's designed to be difficult to find because more and more people on the wrong side of the law are finding the means to hire people to ferret out bugs. So it's getting harder to do. Technology is still always a little bit ahead of counter technology. But for the most part, we're going to show how you can find both bugs and taps with fairly simple equipment. Simple to use, simple to get. It's either fairly low priced or it can be rented and used. We're going to go up through the steps, starting with the easiest, most primitive methods and working up to the more sophisticated ones. You can use all these. Neither one excludes the other. The first thing that's important is physical search. Now I'm going to say this a number of times in this video, and it really is important. It's the number one most important thing of any technical counter surveillance measures group. All sorts of fancy electronic equipment, that's great, it's going to help you find stuff. What if the bug isn't in use anymore? What if the batteries run down? What if the bug's equipped with a switch? So if they hear you searching, they turn it off. This is not outrageous. This is used by the FBI, used by a lot of other people as well. They hear you start a search, they turn it off. No electronic device is going to find that. Physical search is first. Now while you're planning out your countermeasures survey, you need to decide an important factor, and that is, do you mind if the people who are listening know you're searching? In most cases, this should be a yes, you do mind. Because if they hear you searching, if they hear certain telltale sounds, it will show they know you found the bug, it's useless to them, they're going to get in their car and drive away. If you find the bug by yourself without them knowing, you have an opportunity to plant all sorts of false information, feed your competitors or your spouse or whomever things that you want them to know that may or may not be true, or you can simply try and catch them by saying certain things and seeing who shows up, you know, that sort of thing. So we're going to look at both ends of that. But again, first we're going to start with physical search. Now we're in sort of an office environment here. You start with everything available. Start from the top and work down. Particular attention should be paid to anything that has a battery in it or plugs into the wall, especially things that may have been given as gifts. Easiest way to get a bug into a place without committing a burglary, give it to the guy. Hey, here's a calculator from, you know, A&E Printing, where you do all your work. Congratulations. Calculator has a battery in it, could easily have a transmitter in it. They're built that way. Telephone has its own power, often used for bugging devices. We've shown later part of the film how to take the phone apart, look for these devices, some tests to do on them. Do it. But physical search first. Take it apart and look at it. Turn over anything on the desk, any funny looking little things. Where'd this come from? Does it have a transmitter in it? Very possibly. Find out where it came from. Do whatever you can. In some cases, if you want to go to the expense, you can actually x-ray stuff or you can fluoroscope stuff. But usually a physical search will find many things that are there. Here's a typewriter. It's plugged into the wall. What an ideal source. Open it up. Look around. There may be computers over here, local area network. Who uses a typewriter? What an ideal place to put a bug. What a beautiful place to put a bug. It'll pick up everything said in this room and maybe the next one. This particular bug is very powerful. Will broadcast at least 1,000 feet, if not more. And it sits in this typewriter until somebody takes it out. Pictures on the wall. Plants are a real special favor to people that plant these things. No pun intended. Put the device in a plant. It sits on an executive's desk. We've even found people who will place a bug in an envelope, often a special delivery or express mail envelope, address it to somebody who they know is on vacation for a couple of weeks, write personal, confidential on it. Today's bugging units can be so flat, especially if you use a Polaroid camera battery that's a flat lithium battery, surface technology, it feels like a letter. Mail it to the guy, personal confidential, secretary lays it on his desk. It sits there in a very hot area for who knows how long, broadcasts until the batteries run down. Something else to remember when we're talking about bugs is most bugs, especially those that work on a battery, have a limited lifespan. How long? Well, it depends on the bug, it depends on the power output, and it depends on the batteries involved. But it's generally safe to say that a bug will last anywhere from 1 to 3 days. Now this means that most people will not just go in, take a risk, plant a bug, and see what they get. It's not worth that. Most bugs are targeted for specific times. Is there a big conference meeting? Do we have a budget meeting? Do we have a bunch of executives getting together? That's when you want the bug in effect. And that's when you want to look for the bug. Not 2 days before because it may not be there, and not 2 days afterwards because it may not be there. Right before the meeting. Bear this in mind when you do a search. Now this is not universally true. The bug could be hooked up to the mains, the power that comes into the office, just be running forever. But if it's a battery powered unit, it has a limited lifespan, or someone has to come in and change those batteries, taking a risk. So you need to do your physical search. You need to go through every piece of paper, every shelf, every filing cabinet, behind every picture on the wall, baseboards on the wall, looking for wires. We're going to show you in just a second, every suspicious wire must be run down to its source. That is a potential bug. The easiest, most practical way to bug someplace is simply to hide a miniature microphone in the room or in a small hole in the wall near the room. Run some wires out. This doesn't radiate RF, very difficult to find except by physical search. If you find some wires you can't explain, alarm wires, wires in a telephone cable, or just wires running someplace, you must trace them down to their source and make sure it's not a hardwired bug. Past that, we have the RF bugs, and we're going to look at those right now. Now, radio frequency bugs have been around for a long time, and they've changed over the years. They've gotten a lot more sophisticated. The early days, the idea was to put as much power as possible into an RF bug. Now, this is a walkie-talkie, a couple of watts. How far will this transmit? Well, this is a powerful one. This will go 1 to 5 miles. Early bugs were designed with that in mind. Let's send the signal as far as we can. Let's, make the people who are listening to signals safe, get them away. Not anymore. The idea now is to use the minimum amount of power required for several reasons. First of all, the batteries last a lot longer. A 1-watt walkie-talkie will eat batteries up in about 5 hours. A 50 milliwatt bug may go a day on a set of batteries. 2 to 5 milliwatt bug lasts 18 hours, 2 days. Stack a couple batteries, you've got 4 days to a week on a bugging device. The ratio of range and battery power is not direct. There's a formula involved. Just adding more power does not make the range that much farther. A small 5 to 20 milliwatt bug will go 1,000 feet easily with the right receiver and the right conditions. Why do you need more than this? If you need more than this, you put a relay unit in a car, station it 500 feet away, picks up the signal, changes the frequency, rebroadcasts it to your receiver. So today's bugs are designed to be efficient on battery power and efficient on radiated power. This also makes them much harder to find. It's a fact that there are bugs out there, and there are people with scanners now and receivers that can pick up a lot of these frequencies. You put a real powerful bug in somebody's room, the chances of it being detected go up incredibly. A physical search means examining everything, looking in books, under books, behind pictures on the wall. Curtains are an ideal place for a bug. Lamps, behind calendars, any place. There may be a bug. You take the time, go through and look for something that doesn't belong there. Take apart the base of the lamp and look at it. See if there's a little black box in there. See if there's some circuitry that shouldn't be there. This is how you find a lot of bugs. If you had minimal access to a room, say you're in it for 30 seconds or 60 seconds, and you wanted to plant a bug, how would you do it? One of the best ways is go underneath. Go under a cabinet, go under a shelf, a little bit of tape, 30 seconds, and you've planted a bug. Physical search has to include a telephone. First thing to do is to disassemble your phone and look for things that shouldn't be there. This is known as the strip search or the sneak and peek. You need to check out the button, make sure it looks okay, feels okay. You need to look behind it in the handset and make sure nothing is hanging on the wires or stuffed up inside the handset itself. The correct way to completely disassemble a phone is to get two phones that are designed in the same manner. Take it apart, make sure the phone you know is clean. It has no extraneous materials, nothing's hanging on it, nothing underneath. Look for small taps that might be hidden from view underneath the circuit board. Now take the phone in question, disassemble it, examine it, and compare the two circuits. Immediately in this phone, we notice extra circuitry that our clean phone didn't have. This is an infinity transmitter. This one is built in. It looks very much like phone company equipment. Be very hard to spot if we didn't have the other phone to compare it with. A regular search would not turn up anything unusual. This is a close-up of the infinity transmitter. We can see the workmanship, how hard it is to find. Now remember, bugs can be underneath the circuit board, attached to the board itself, or anywhere in the wiring so they look like they're part of the original circuit. What happens in your physical search if you find a couple of wires? Now these of course are thick AC kind of wires, but even if you find thin wires, they disappear into a wall, they go away. You need to trace every wire you find. How do you do that? What if the wires go into a cable that holds many wires of similar shape and size like a phone cable? Well, the easiest way to do it is this thing, made by Triplet Corporation. It's a tone generator. Gives you a low tone, high tone, or a warble. Along with this, it's called the Fox, comes a device called, oddly enough, the Hound. The Hound is an inductive amplifier. It does not have to be connected up to the cable. If I take this unit, connect it up to the two wires I found, put the tone into the wire, take this unit, and lo and behold, I can follow the tone. What happens when it disappears into a cable? I can follow it all the way down the cable. This is good for a number of miles. You can follow the tone down a phone cable or a cable like a phone cable for miles. Even if the cable disappears in the wall, as long as I'm still fairly close to it, I can follow it inductively with this amplifier. These are about 85 bucks from Jensen Tool Corporation, made for telephone linemen, telephone installers. They're several $100s if you buy them from commercial countermeasures suppliers. Buy them from Jensen. The simplest, easiest, first step for finding a bug is to take an all-band radio, turn the volume up high, and turn through the bands. Now, the way we're doing this, you have to remember, is going to alert anyone who's around because they're going to hear us doing this. I could take this radio outside if I wanted to, or put headphones in it, and just listen and see if I picked up the room noise. But the easiest way to find a bug is to take an all-band radio, turn the volume up, walk around the room while you tune through the channels. So to use the all-band radio as a device to find bugs, we want to turn the volume up loud, put it in the room where we think the bug is, if we don't mind alerting the people who might be listening, tune through all the frequencies. Now I have the little Coney on behind me. I happen to know where it is. Now when we run across the frequency, just even within 10 feet of the bug, we'll immediately get what's known as feedback. My God, there it is. As we tune off just slightly, you should be able to start to hear my voice. Right as the feedback falls off, you can hear my voice coming out of the radio. But we're so close to the bug in this case that we're just overpowering it. Now, the good part about this is little bugs don't have coils to suppress harmonics. Harmonics are doubles and triples of the original frequency. And they also put out a lot of scatter, little spikes of signal in other parts of the band. Now, if we go way up this, we may find, that was probably the primary frequency because it was so good, so loud. We may find more feedback someplace else on the dial. What this does, sounds like we've got it right there next to the weather band. Makes it kind of hard to listen to. But what this does is let us find the units. Got a little feedback right there. Hear that? Here we go. This makes it a lot easier to find the unit. So we have to go through all the bands and see if we get that howl. It means there's a transmitter in the area. That's the only thing that will make that feedback noise. One of the first units available for commercial debugging was a modified field strength meter. Well, this device was supposed to sniff out bugs of all frequencies. The way it did that is it's basically just a diode. It's a crystal set. It's a diode, a coil, a small amplifier that powers the meter. Look at the back, we can see there are very few parts in it. Here's our little diode, here's a coil, there's a little amplifier, potentiometer, meter, and an antenna. That's about all. Sold for a couple $100. Did they do anything? Well, yes, they'll detect radio signals just like they're designed to. In fact, if you took this out into the Sahara Desert, far away from any radio stations, and looked for bugs, you'd find one if there was one there. Our problem is that we live in a area that's saturated with radio signals. Our spectrum is very crowded. In fact, in this particular room, we're sitting about a half a mile from a 50 kW AM station that beams right through here. I pick it up on my answering machine very clearly, whether I want it or not. So what happens when I turn this on? When we turn the meter on, whoa, we have signal. In fact, we've pinned the meter. Of course we have. We're sitting on top of a 50 kW rock and roll station. Now, if I extend the antenna, decrease the sensitivity, and put it back by a bug that I know is working, I can get the meter to vary maybe 1 degree. Look at that. Look at that little teeny jump. That going to tell you you've got a bug there? Basically, field strength meters are pretty useless in today's environment for searching out bugs. And no matter how much they cost or who sells them, I don't think I'd buy one. You're looking at a scanner. It's an ideal unit to pick up most bugs. Scans through the frequencies I've set in it till it finds something, locks onto it. They're getting much more sensitive. A hot scanner, and this Bearcat is a very hot one, has a sensitivity of below 3 microvolts, maybe down to 1 microvolt. So pick up very low-powered bugs as long as you're on the right frequency. Where are bugs located? Well, if we start down at the bottom, you can find some AM bugs in the 160 to 190 kilohertz range. These include carrier current transmitters, which we'll show you in a minute. Scanner will not pick those up, although it will detect some AM signals. The lower bands will not pick up those particular bugs. From 116 to about 30 megahertz, we have the high frequency band, or short wave. Here we've got ship to shore, air to ground, international flights, worldwide communications. It's unlikely you'll find too many bugs in this area because you have to have a very long antenna to make them effective. There's lots of noise on the bands, and the signal strength of everything else on those bands is quite high. We have everything from multi-kilowatt transmitters in Moscow, Voice of America, etc., transmitting here, and it makes it really difficult to isolate and receive, especially over a long period of time, a small bug. There's also a great deal of noise in these bands. Computer noise tends to be in these bands. So we don't find a lot of bugs in those particular bands. Generally, to find bugs, we want to look above 30 megahertz. Now, 30 to 50 is what we refer to as low band. We have public service in that band, some police departments, things like that. So we get up to 50 to 54, we get a ham band. 54 to 72, we hit some TV channels. 72 to 76 is a low-power band in which we'll find some devices. There are wireless mics that fall in here, and it's an area that most people don't realize exists. because of that, the DEA uses it. People that don't want to be heard often use this particular band. So it's actually a good place to put transmitters. Now we got to say something here. Most scanners on the market cover only certain frequency ranges. So there are still areas that no scanner is going to hear. Now recently, ICOM and a few other people have introduced continuous scanning scanners that go from, say, 1 megahertz to a 500 or 1000 megahertz without skipping a single band. These things are ideal for locating low power transmitters, for listening to bands you can't normally find on your regular scanner, for finding units. They're more expensive, of course, and they're just coming out, but they're a really good unit. From 76 to 88 are our last two TV channels. 88 to 108 is the standard FM broadcast band, which doesn't come in on the scanner, but will come in on the radio. Most of the units you buy, for instance, if you want to bug somebody, you go to Radio Shack, you buy the little units they sell, they're going to fall into the commercial FM band, 88 to 108. This is good because any receiver will pick it up. It's also bad because any receiver will pick it up. Your neighbors can hear it. Some kid tuning around can hear it. It's going to be all over the dial. You can stick a screwdriver in most of these little devices and tune them right above or right below commercial band very easily. This makes them extremely difficult to find, and you need to do the same thing to receiver, of course, in order to receive it. Because of that, we do find units in the commercial 88 to 108 area. From 135 to 138, say in that range, we have satellites. Not much else. This is a real good place to plop a little something, because even if somebody who's a scanning freak hears carriers there, they're going to figure it's a satellite or some other balloon monitoring device, something like this, and they won't be alerted to it. Now, of course, if they hear confidential information, that's not going to hold true, but if they hear a carrier, it's not going to bother them. So we get up to 151, 174, we're in high band, commercial government area. It's divided in half. From 151 to 162 is civilian, from 162 to 174 is federal, usually non-military, but federal. From 174 to 216 are TV channels 7 to 13. TV is good and bad from the standpoint of placing a transmitter. There's a lot of stuff going on in the spectrum. It's hard to find the transmitter. And the channels are very wide. That's why you can sometimes hide a small FM transmitter in the bandwidth of a commercial TV transmitter. And people generally don't look there. It makes it very difficult to find. You've got to be pretty good, know what you're doing to find it. The area between 216 and 220 is an open area. It's rarely listened to by anybody who has a scanner. Typical scanners, for instance, this Bearcat's tuned from 30 to 50, 118 to 136. Then they jump over to FM because they've been using AM in the lower frequencies. And they go up quite a ways, say from 406 to 512. Now the newer ones cover the 800s, 802s to 960s, where the cellular telephones are. But most of them still cut off at 912 or 915, something like that. So you have to remember that. This is a frequency counter. It's made by Optoelectronics. Good unit, good company, a couple $100. Its range is 1 megahertz to 550 megahertz. Now the sensitivity will vary some in that range, but it works pretty well. Now we've taken the liberty of mounting this unit, which you see here. This is about a $70 amplifier. It's a preamplifier, often called an active antenna, which is not really what it is. But it increases the gain somewhat. When we're looking for real little transmitters, like we are, it may give you another foot of range, which is very important. So we recommend this. Also, you can put this on your scanner. It gives you better front-end reception. When you turn the frequency counter on, you see it's sort of changing numbers here. It's self-oscillating. It's trying to be so sensitive to all frequencies that it's just sort of ranging itself. That's okay. That's one of the things we use to find bugs. Frequency counters are not nearly as sensitive as radio receivers or scanners, just inherently. A counter has a broadband response. That is, it's sensitive to all frequencies at the same time without having to be tuned. A radio receiver can only be tuned to one frequency at a time. The radio must be retuned to receive a different frequency. The tuning, however, permits the radio to be very sensitive at the frequency it's tuned to. Receiver sensitivities can be well below 1 microvolt. The counter, on the other hand, must be close enough to the source of the radio frequency transmission to pick up enough signal to let it count. In the old days, lab counters, which worked on benches, were not nearly sensitive enough to pick up the units we're looking for, but these new devices, such as this little one, are, especially for the price, very good little unit. The counter is so sensitive that it can't help but self-oscillate, as we see it doing now. The only way to stop that would be make it less sensitive. The counter can be used in the presence of major radio signals. As I've said before, the room we're in has a very heavy AM beaming through it because it will only pick up within a certain radius. It also has a built-in separate detection circuit that can be adjusted up here for a threshold, and when it's in the presence of local RF, once you get the threshold underneath the resident RF, this little light will come on when you're in the presence of RF. However, we found this is not the best way to find a bug. Paying attention to this counter is the best way. Now, when you get used to using this unit, you'll see it self-oscillating. When you turn on a bug, it will grab the and it comes within range, it will grab the frequency and it will hold it. This does a number of things. It tells you there's a radio present, it tells you you're close to it, and it tells you the exact frequency of it. So you can then verify that it is a bug by dialing it up on a scanner or a receiver that receives that frequency and listening to it. All right, I've turned on this transmitter here, and I happen to know it's in the FM range. Let's move the unit. Out here we can see the unit still self-oscillating. As I move in towards the transmitting antenna, slowly moving it around, suddenly it locks. And the RF light came on. Very good. I'm in the presence of RF. It's at a frequency of approximately 90.56 megahertz. As I get closer, I see that it locks on that frequency. I can tell that this unit is functioning. That's how you use this unit. You sweep around the room, rubbing the antenna over everything suspicious. Suddenly it locks on, moves slowly. It's locked on a frequency. Now I can verify that frequency using a receiver or a scanner. It will only read one frequency, by the way. If I turn another unit on that's more powerful, immediately it goes to the more powerful unit. This is at 170.851, the exact frequency this wire is transmitting at. Also shows the presence of RF. Now this is a more powerful unit. Let's see how far away we can get it and still read it. Nice and slowly, I'm going to move it up here. Okay, I'm 4 or 5 feet away. We're still reading it. Still reading it. Okay, we broke a little bit right there. That will read this more powerful unit about 4.5 feet from the unit. It locks up, the RF light comes on. Very important things. This unit will let you sweep and find most RF transmitters. Once you have a little practice with it, you can watch it lock up, you know something's there, you can turn on receiver and verify that. In a demonstration of how to verify a frequency. Okay, we've got a signal, we're not sure what it is. We read it on the counter, 17850. Okay, we take the scanner and dial in 17850. Now, in theory, if there's a bug nearby operating on that frequency, or any other transmitter for that matter, I should be able to pick it up on the scanner, and I should be able to hear what it is. Now, of course, if we're close to it, we're going to get our feedback howl, and I have to move the scanner away. The scanner is easily overpowered because it is very sensitive. But let's try it. Let's turn it up now, see what happens on that frequency. By God, there's our howl, all right. As I move the scanner away, we can hear my voice coming through quite clearly. We hear the device howling, even as it gets several feet away. We can use this feedback technique to help locate, hear my voice coming through the speaker, to help locate the source of the bug quite efficiently. Just like we can use the counter by moving it in and out, watching the RF detection light and watching where it latches on. It gives us the frequency. This gives us an option to back up the frequency and prove that it actually is a bug. Very efficient system. Very cheap. This is far less. These two units together are far less than the price of a normal Countermeasures scan. And these can be reused over and over. A dynamic pair to use together. Let's talk about telephone taps for a minute. Got a number of different ones here in front of me, different varieties, RF, direct. I also have a lovely little device, about $45 from a popular mail order company called a tap detector. Hey, 45 bucks, you hook it up to the phone, a little red light comes on, shows you've got a tap on the line. Solves the problem, right? No, not really. These are a little better than useless. They will sometimes, on a good day, if your karma is right, show if an extension phone is picked up off the hook. Or if you're in a hotel, they will sometimes show if the PBX operator, if it's an old-fashioned PBX, plugs in to listen to your phone calls. That's about it. Don't ever depend on something like this. 45 bucks, nothing is going to tell you if your phone is tapped. In fact, let's face facts. To be real honest with you, there's nothing on the market today that will tell you electronically if your phone is tapped by a professional. Ain't going to happen. There is nothing. One step down, device called a TDR, Time Domain Reflectometer. It's pretty good. It's a very expensive unit. It's very hard to use. What it does, sends a little pulse down the wire and looks at the reflection, just like radar. Shows every junction, every solder joint, anything that's clipped on the wire, every appearance appears on the TDR's screen. Does this mean you can just hook it up, look at the central office, see if anything's on your wire? No, it does not. It means you have to hook it on your phone wire, learn how to use it, go to the first junction, look at that junction, short it out, hook the TDR up there, go to the next junction. You may have to go to 3 frames offices before you hit your central office. You have to know somebody to get them to connect across the frames offices. It's a very difficult device to use. At best, it will find things if you're able to go isolate every appearance, look at the TDR, figure $8,000 to $10,000 for a good TDR. It will not tell you if somebody decides to bug your phone 5 minutes after you take the TDR off the line, nor can you leave it on the line and watch it. It's not that kind of device. So we're not using a TDR. There are a number of other tests that will find most bugs, not the top, not the professional, not the stuff the FBI is going to put on at the central office. You ain't going to find that. That's life. Bear that in mind when you talk on the phone. However, if your threat assessment level is lower than that, if it's a business partner or a spouse, a private detective, we got a good shot at finding it. Again, physical inspection is very important. Take the phone apart, look for everything. This is an appearance box. This is the first appearance of our phone line that we want to test. Now, as you can tell, a lot of lines come in here. How do we find our line? 2 ways. The easiest, find a friendly phone guy, have him look it up in his book. Can tell you exactly where your line terminates in these contacts before going on to the CO. Second easiest way, we've installed our little oscillator at the house. We have a tone on our set of wires. Here's our inductive amplifier. We can run it through the wires, looking for our tone. Then we can test all the contacts out until we hear our tone just by running it near the contacts. Now, I happen to know ours is located right over here. And there it is. There's our tone. You hear it in the background there? It's kind of weak. There's our tone, so we know these are our contacts. Once we've identified our contacts, we jump them with a little jumper cable across the contacts. All we're doing is shorting it out to itself. This allows us to go back to the house and take resistance measurements on this wire. Now, you've seen us go down to our first appearance and short the wires out. Why did we do this? Well, we plugged a little parallel outlet in here so I can measure the resistance between here and my first appearance. Now, I know the 24 gauge phone line is about 14 ohms per 1,000 feet. So if I click this on and read the meter, it's about 34, 35 ohms. Now, I can mentally calculate the distance to the box and back and see that that's just about right on. There's nothing drawing more resistance than it should on this line. It's a good sign. Doesn't prove anything positively, but it's a good sign. I can also record that number and check the line from time to time. If the resistance jumps suddenly, especially an increment of, say, 80, 90 ohms, got a problem. Follow the line down, find what the problem is. Good chance it's a series bug drawing power, adding resistance to the line. Now, we have 2 types of phone devices, parallel devices and series devices. The easiest way to tell the difference is all parallel devices, or almost all, use a battery. This is a parallel device. This is a parallel device. You see where the battery hooks up, even though it still clips across the phone wires. Draws its current from the battery. This limits its lifespan, but makes it much harder to detect. Series devices draw current and are easier to detect. Parallel devices have their own power source. Some parallel devices have a battery and trickle charge off the phone wire, so they actually charge the battery when the phone's not in use. This is about the best of 2 worlds, something that will do this. Long range, long power, very hard to detect. Series devices that do not have a battery but have clips or wires to be hooked up to the phone, Sheffield Electronics again, Deco Electronics, Consumer Magazines. These, you have to break one side of the ring or tip wire, usually the red wire, and hook them in series so they draw their power from the phone line. Even though they have two little clips, to break the wire, hook it in series. It doesn't have a battery. They do draw current from the phone line and are a little bit easier to find. The next measurement we're going to do is on-hook and off-hook voltage. This is an important measurement. Now, we've unclipped our little jumper cable, so the telephone is back to its normal everyday use. It used to be that the voltage was very exact and any deviation meant you had a problem. Phone companies in those days ran on a backup system that consisted of car batteries. Today they run on electronic systems with generators, so the voltage is not quite the same all over the country. The important thing is that every time I measure this voltage, it should be the same. And any other telephone line coming from the same exchange, the first three digits, the number is the same, should be the exact same voltage. If I have two lines in the house, check them both. If not, go next door, go down the street, check it. Should be almost identical. Any deviation, say a volt or more, means there's something drawing power. Could be a bug, could be a short, worn wiring, but it's something to check out. Okay, the on-hook voltage here should be between 48 and 54 volts. We're going to check that out. You can see I plugged in a little parallel connection that just sort of opens into spades here. Got the multimeter set up. You're going to check between the tip and the ring, which is the red and the green wires, and see what the voltage is. And as soon as I manage to hold this correctly, you'll see the on-hook voltage, and this is 50.6, which is just exactly in the range. That's real good. I'm going to take the phone off the hook, measure the off-hook voltage in the same fashion as I measured the on-hook voltage. And we see that that is about 5.6. Again, very legitimate. Everything looks okay. I'm going to record those voltages in my little log and check them later. There are a number of hook switch defeats popular with eavesdroppers. Now what these do is basically short out across the hook switch. So even though this telephone is sitting on hook, its very sensitive microphone is picking up all the conversation in the room and sending it down the wire. As an eavesdropper, all I have to do is go out someplace along the line, tap into the wire, amplify it, and I'll hear all the conversation in the room. There are a lot of ways to do this. The infinity transmitter is a good one. Also, you can set up high voltage devices, so if a pulse is sent down the wire, it turns on automatically. I can pick it up. A relay, transistor, diode, lots of ways to do this. So what you want to do is go to the wall, or at least go right off the telephone as we've done, leave the phone on hook, and search these wires for room audio. Now if I can hear myself, or in this case a noise source, I'm going to use a local radio station, if I can hear myself coming down these wires, we got a problem. Doesn't mean you're being tapped necessarily. A number of modern electronic phones, not this one, but electronic PBX phones, are carrying room audio even though they're on hook. It was just easier to do this in the design stage, so the manufacturers left it alone. Design defect. Anybody who can get access to that wire in the house or out of the house can pick up all conversation in the room or the office. Probably 40% of electronic PBX phones broadcast while on hook. It's also possible that some other component in the phone is broadcasting. There was a popular phone a while back that was in the shape of a duck. Just a quack when it rang. Well, the quacker, the transducer, was an ideal microphone and was online all the time. And eavesdroppers figured this out pretty fast. So what you want to do is get a little amplifier, powerful little amplifier. Now I've hooked up to a speaker. Normally, of course, you'd use headphones. Give yourself some room audio and check every combination of the wire. Now it's important you don't just check the red and the green, because if I was going to send conversation down this wire, I wouldn't send it down those two. It's too obvious. I'd pick another pair, maybe the yellow and the black or the green and the yellow, that you normally wouldn't suspect because some people wouldn't check it. If the phone is a multi-wired one with a cable, I use any two I could find. Most cable phones do not use all the wires. Even these have two spare wires. The yellow and the black are not used. So there are two free wires for me to send conversation down the hook. So let's turn up the room audio a little bit.
They're going to make a good draft. I mean, Nelson has never...
And we'll listen to our...
...badly on the draft. You could say Thomas Frank was a miss, but there was really nothing in that draft that anybody could have done.
Obviously, we're getting room audio down the wire. Now, I've shorted the hook switch in this so that would happen. we've got a problem. That means replace this phone, throw it away, tear it apart, and find what's going on, or treat it as a hot phone and feed false information down it. There is one test we can do with our trusty digital VOM that will give us a good indication of either a series or a low impedance parallel tap on the line. To do this, the first thing we have to do is run a wire to earth ground. Now we've taken this wire and run it outside and hooked it around a cold water pipe that goes into the ground. This is a real ground, an earth ground. Now, with the phone on hook, I'm going to measure both the tip and the ring, that's the red and the green, voltages. And I'm going to write them down. First of all, let's measure the negative, or the ring side. This should be just about what we had before for full battery. In other words, about 51 volts, and that's what it is. Now, I need to set the range of the meter down to the millivolts. Take the red wire, which is the tip side, measure that. That should just be a few millivolts. And it is. I need to record both those. Once I have those readings, the next step is to make up a jumper wire like this, two identical 2700 ohm resistors right here. I've soldered them together, so we have a center place here, two identical resistors, and a clip lead. I want to open up the telephone here, or actually pair the wires, go across the red and the green, clip these leads on. Now that's going to give me path of the voltage between these resistors. And the next thing I want to do is measure the voltage from the center tap of these resistors, right between them. And I want to use very good tolerance resistors here, very close. 1% if you can get them is real good. Measure the voltage from here to ground and write that down. Now this is, in effect, terminated the phone line, and the voltage I'm going to measure here is going to be negative and will be 1/2 the quote battery voltage of the phone line if the lines are balanced. Now that's what I'm trying to find out. Are these lines balanced? Now the other measurement I can do here, which is going to give us a little more detail, is to unhook the tip side, rather the ring side, and hook this in and measure current flowing through here. The same way I can measure current from the center tap of the line. Now, if you're not familiar with current, you always have to do it in series. So I've got to actually clip the wire or unhook the wire, hook this in series, measure current flowing through here. Now what do I want to do with these measurements? It's a little complicated, so we're going to put it up on the screen here. The first step is to take the voltage measurement from our real ground to the center tap of the two resistors and double it. Now we need to add the voltage measured from our true ground to the ring wire to the voltage measured from the true ground to the tip wire. These need to be added algebraically so we keep the signs correct. Now we need to find out the difference in these two steps. This will be a small figure which we will take and divide by the current we measure flowing through our resistors in milliamperes. The result will be the true difference in both sides of our balanced loop. This difference should be quite small. If it's greater than 90 to 100 ohms, our line is very unbalanced, and there's a strong possibility of a series tap in the line. Here we're set up to measure current draw. The wires are split, so we can hook the meter up in series and measure current draw. Now with the phone on hook, there will be no current drawn because nothing's happening. When I lift the phone up, we're going to get a reading, establishes how much current is being used. This is not indicative of itself, but should be recorded. It's important to see the difference. Now I have a series phone tap right here. I'm going to hook it across the wires in series with the phone and see if we can tell that it's drawing current. Now this is a very small unit. It's a microelectronics. It's going to draw very, very little current. It's going to broadcast a couple hundred feet, both sides of the conversation, when the phone is lifted up. Let's see if we can tell with our meter if it uses current. And by God, the reading is different. We can tell something has upset the reading. It's drawing current, which it wasn't before. Something is in series with the phone line. This is just one reading that you can take, but it's a good reading. It will not show up a good parallel tap that's self-powered, but any unit which is a parasite that draws its current from the phone line should make a difference in the current draw on the phone line. It's good to record this every so often and compare it. This device is the next step upward, financially and in the areas of sensitivity and selectivity. This is from Research Electronics Incorporated, REI. They've been around a long time. They've designed a number of things. This is known as a CPM 700. What it is a broadband receiver. It doesn't have to be tuned. It has a number of very unusual features. This is in the 1,500 to 2,000 range, but does a lot of things that more expensive equipment will not do, and does them well. First of all, if we look on the front of this, we'll see we have power, we have a number of controls. The device can be put in one of two modes. In the search mode, we use our wand here, and we notice, you'll see in a second closer, we notice the scale in front, the little bar graph. This tells us the relative RF intensity in any particular area. We walk in a room holding the rod vertical, study the little graph, see what the RF intensity is. Then we can start an electronic sweep by moving this rod around. This runs on NiCad batteries, by the way. In the search mode, we can walk around until we get a high reading on the graph. We can actually localize, we can decrease sensitivity. We have a switch in front with a high that makes the sensitivity much higher by pushing it in, almost too high to use in this particular environment. And we can also decrease sensitivity by folding the rod up. These features allow us to pinpoint the location of an RF source. Now, in the search mode, we still can use the gain control, which will output through a speaker, which of course will give us our feedback if there's a device in the area. We'll also alert the people listening to the device that we're searching. Or we can plug in these headphones you see around my neck in the front that cuts out the speaker entirely, so you don't hear someone searching for the device. Now, after we're done with the search mode, this has another unusual feature. We can push a button in front and put it in the monitor mode. When it's in a monitor mode, we can just let it run. We adjust the gain, the threshold control rather, for the average RF level in a room. The machine does nothing, it sits there. If the level suddenly goes up, somebody walks in a meeting with a body wire on, for instance, or someone turns on an RF transmitter in the area, the threshold control will go overboard, will show us by a pulsing light, and if we so desire, if we turn it on, by a beeping tone that there's been an addition to the room. There's a new RF source in the room. And we can put it back in the search mode and go find it. Or we can simply listen with the headphones and verify that indeed it is a bug or that someone's wearing a wire. So the machine actually has several functions. Besides that, it has specific probes to do specific jobs that other, more expensive equipment, again, doesn't have. You can see the various features of the REI device facing you. Now, the bar graph showing us not much going on. We're in the search mode. These little outputs give you what mode you're in, various other information. We don't have much going on. The level in the room is obviously low. Now I'm going to reach over and turn on a law enforcement bug, and let's see what happens when I do that. I'm extending the probe, and I'm moving towards it. As you can see, as I come closer, it's a physical description of the RF in the room. Not only establishes a level, I can decrease the sensitivity a little bit if I want to, or I can reach down here and with a flick of the switch, I can turn the gain on high, and look what that does. Even with the probe entirely collapsed. Now I'm about 4 feet from the bug, 3 feet from the bug, 4 feet, 5 feet, 6 feet, 7 feet, This is the kind of reading. Look at that. Look at how on the high sensitivity, how good that is with the probe collapse. Now if I extend the probe, it's just overwhelming the unit. So what I'm going to do here, let's go back to lower sensitivity. Now still, I can see as I walk towards the unit, I can just watch the signal strength increase. Now, if I want to know if this is, double check this is a bug or not, I'll turn on my audio. Now, of course, in most cases, I would do this with headphones. There's our traditional howl, and you can hear my voice coming through very clearly. This is proof of a bug. The feedback howl, sound of my own voice coming through the device, is proof that something in the room is feeding back and recycling on me. Now we're getting a local radio station when I touch the probe because it's using me as an antenna. But that obviously, right there, very good. Wave it around, get it very nicely. You can see the signal strength. I can locate the bug by moving the probe around. Now, I would not use the speaker, of course. If I didn't want someone to know I was searching, I would have used headphones for the same sort of thing. You should always do random follow-up sweeps based on various considerations. Whether you find a bug or not, do more sweeps. Don't let people know when you're going to do them. And even if you find a bug, you don't stop there. A good eavesdropper will often plant more than one bug. For instance, take this little FM unit here, commercial FM unit, turn it on. Lovely little thing, easy to find. Now, we can see on our bar graph, getting readings on it. Okay, I want to verify that that's what it is. I'll lean forward here, turn on this. Oh, there's our feedback howl.
Shopping spree.
Decrease the sensitivity a little bit. Listen to that. Proof that a bug is there, but that's not proof that that's the only one. Maybe I've hidden this so you can find it easily. And then maybe I've taken a better unit, maybe a remote controlled unit, and hidden it so it's going to be a lot harder to find. Well, if you're a security service or security manager and you find this, you've got proof. You can go and say, look, we did our job. It may not be the entire job. Keep searching. After we've used the REI device in the search mode, we can then flip over and put it into the monitor mode. Once in the monitor mode, we get a nice readout of the threshold. And we can adjust our RF threshold until we see the device or hear the tone. And this is just picking up ambient REF. We don't want that. So we're going to adjust the threshold up till it's just over that. Now we can see in the bar graph where I've got the threshold adjusted. I can actually go all the way up here if I want. Doesn't make any difference. But the most sensitive place is right before it detects the ambient REF. I'm going to turn on a unit. Look what happens. The unit is several feet away. Get a nice clean reading. So you can turn this on in your office, let it sit, just let it run. Somebody comes in wearing a wire. Somebody turns on a transmitter. You'll be alerted. I'm going to toss this device to my cameraman, who's out of the picture, and have him walk slightly away. Now, we've lost him a little bit, you'll see. We're going to go vertical on this. We're still getting him. I haven't touched him, and he's about 6 feet away. Now we've lost him. I'm going to switch this over to high. See what happens there. Look at the RF spectrum. Look at how we flooded it. He's about 12 feet away, 15 feet away, almost 20 feet away, holding a small law enforcement type medium to low power bug, not a high powered body wire. Now if I go low on this, well, we've lost him right there. We're just on the threshold of him right there. You can see that. As he moves around a little, we pick it up. If it's irritating, we turn it up a little bit, go to high, there it is. Now this is a long way away. This is a very sensitive unit. It's a very nice mode. Leave it in the monitor mode, let it do its thing. Gives you a good indication of what's going on. We're using the CPM 700 in a search mode now. Got this collapsed. You can kind of see the bar graph. Not much going on here. Got the unit in the same place we had it in for the counter. Let's see what happens. We're going to extend this out. Gives us some sensitivity. We look like we're getting a little RF. As I move over, look at the bar. Immediately starts bouncing up. I can localize. I can come back here. It's going down. I know that's not the right direction. Down here, nope, not the right direction. Up here, look at the increase in signal intensity. Right there, I know I'm hot. Go over here, and immediately it starts backing off. Very nice. You can tell. I can pinpoint it. I know it's in this box. I can pinpoint it just within an inch or so by moving this around. The probe is about 6 feet from the bug. We have little or no indication on the bar graph. As we move closer, immediately the RF reading picks up. I'm now about 4 feet away, 3 feet, 2 feet, 1 foot. I'm touching the book behind it, and I can tell by watching the display. Now I'm moving away from it. I'm about 3 inches farther away, 5 inches. Look at the RF go down. This helps me pinpoint, localize exactly where the unit is. I can get it down to within an inch or two in any direction. I'm moving the probe down now away from it. RF dies off. Move the probe up away from it. RF dies off. Let's put it on high gain and see what happens. Saturation. Even if I come way back here, the probe is extended as far as we can from the thing, about 6 feet. We can still tell that there's RF. As I move closer to it, immediately we've saturated it. If we turn it up, hear the gain. We can hear our feedback. We can hear my voice coming through the unit. So I move back. I can decrease the gain to help me pinpoint the location of the unit. I've had it on high. I know there's something there. Where's the highest RF? It's right there. Let's turn it up and see. My gosh, there's the howl, there's my voice. We have pinpointed the unit right within an inch of its location with the use of the REI CPM 700. This is a parallel phone tap. It has its own battery. It doesn't draw any current from the phone line, doesn't reduce the voltage, doesn't add much resistance. Very difficult to find with conventional means such as an ohm meter. Best way to find this, RF detector. Let's start with our little optoelectronics. When I turn it on, you may not be able to see it, but it's just ranging. It's just self-oscillating. As soon as I pick up the phone, the RF detector comes on and it latches on to 168. I know by going near the phone line and picking up the phone and watching this latch on that I've got RF in the area. I can pinpoint the location by moving back and forth just as we have with the other RF bugs. Now, of course, an even more sensitive method is to use our little REI detector. Again, it's just ranging. You can see by the bar graph there's not much RF in the area. If I pick up the phone, immediately it becomes saturated with RF. I can use my verifying control, hear the dial tone, hear the howl nice and loud, or since I've already located the frequency and set the radio to it, I can simply turn it on, and there's our old friend, the feedback howl. By using the frequency counter or the REI RF detector, you can find it easily. Now, as soon as I hang up, signal disappears. Be sure you utilize that factor when you're looking for taps. Electrical outlets are one of the first places to suspect any sort of surveillance operation. First thing you should do is go to the circuit breaker. Turn the current off so it's safe. Take this apart. Look on the back for any extraneous circuitry that could be a transmitter. Look in the hollow wall. That's a favorite place to leave a transmitter. Clip it across the AC, drop it in the wall. Got a nice shot into the room. It'll run virtually forever without a battery change. The next thing to do is take your counter and check for RF energy. You'll notice it's free ranging. There's no extraneous energy here. We're okay. To verify that, we'll take our REI counter, grab our wand, and run it around the plug. No indication. Nothing's happening. We have no RF within the range of the unit emanating from this socket. Another room attack, a great one for bugging, is to take a transmitter that effectively transmits over the wires in the wall. Our good friend Radio Shack is the main source of these units. This is known as a carrier current transmitter. It's plugged directly into a socket. It blocks out the AC from the socket, picks up room audio through a small microphone, transmits extremely low frequency RF through the wiring in the house. How does this work? Well, it comes with a receiver that matches it. This receiver can be plugged in another outlet as long as it's on the same wiring pattern as the transmitter. This means in a house where you have two-phase electricity, you've usually got two wires coming in with 110 on them and one common wire. You've got a three-wire system. You need to check several outlets to make sure that no transmitter is plugged into one phase. If I'm in the wrong phase, I won't receive the audio. In the old days, the audio would stop at the local transformer that PG&E puts on the pole. That stops audio. Nowadays, PG&E is strapping most of their transformers, at least in big cities, so they can run their own audio down the wires and or use load monitoring systems so they can tell how much electricity you're using without coming out and reading your meter. What this means is there may be audio on the wires in your wall. How do you check for this? This is a great little device. One of the things people do with this is take it, remove the cover, put this circuitry, which looks very innocuous, into a stereo or a television set. Who's going to notice this if it's laid across the AC in an already existing unit? Very difficult to find. How do we test for a carrier current transmitter? Well, the first thing, of course, we can look at is our frequency counter. And unfortunately, it won't lock up. It doesn't go low enough to detect the very low frequency of a carrier current transmitter. It's just kind of wandering aimlessly, no indication from the wiring. The next thing we can do is try our old friend, the REI unit. This has a special low frequency probe. Comes with the unit. We can put this in the socket and see if it'll pick up RF. Obviously, right away it does. You can see the strength on low gain. If we put it on high gain, it saturates the unit. The transmitter is hooked up across the room at the moment. This is the reading we get, and we can verify it by turning it up. We're using a radio as a sound source, and we turn it up. We hear the audio coming cleanly through the REI unit. Very handy unit. Is there an alternative to this? Only one. Most of these units, as I mentioned, come from Radio Shack. Spend $80, $100, and buy Radio Shack's wireless room monitor and their wireless babysitter. Most units on the market are going to be Radio Shack that someone has spent 80 bucks for and plugged into your circuit. Plug in your own receiver and see what happens. Turn it on, and by God, there's our feedback loop, as well as our test audio. We know that audio is getting into the wiring of the house from somewhere simply by using this. Sometimes you may also pick up PG&E talk, other noise, but the important thing is we hear the room audio. If we turn it up enough, we hear the feedback loop. This will not find everything. If a unit is custom made and is on a different frequency, this won't find it. But I tell you, 90% of all units out there are Radio Shack realistic room monitors. Run it up and take a look.
I'm going to talk about receivers, both manual and automatic. Where most people are familiar with a manual receiver. The automatic receiver is more commonly called a spectrum analyzer, but they basically do the same thing with the same kind of operation, and I'm going to explain the difference between the two. We'll start with the manual receiver. I have here an ICOM receiver, which is representative of a good but not great VHF receiver. This one tunes from 30 megahertz through above 1 gigahertz and covers the bands you commonly would find for transmitters. And like the receiver, it has a knob which you tune with. This has a digital display of actual frequency, a whole bunch of other knobs that can do some special features like scanning, which we're not going to talk about. And you can also directly enter frequencies from the keypad. I've tuned in a local FM station here. In FM broadcasting, that's generally called wideband FM, which is designed for high fidelity type operations. Most communications applications tend to be narrowband, and so receivers will have a switch to select between wideband and narrowband. And we're going to select a weather station here. I'm using the keyboard because it's faster, although I could dial it. We listen to in wideband. There's hardly anything there that sounds like there's just noise, and some modulation may be buried. We select narrowband. You can hear it quite clearly. So you have to match the bandwidth of the receiver to the application you have in mind. And most hidden transmitters tend to be narrowband. A receiver, by its inherent design, only receives one frequency at a time. And here we're listening to the weather transmitter. If I wanted to listen to something else, I could tune across and stop at everything that might be interesting. And it takes a long time to cover the band. Now, if I were to manually tune across the band as I'm doing here, and every time I receive something, well, note the S meter reading and the frequency, and continue on scanning across the band in either direction. I'm going down now. I would end up with a chart of frequency versus amplitude of this particular part of the band. Here I'm in the high VHF band. I can make it a little bit more convenient by going through the broadcast band. There's more things that are readily available there. The reason why I'm going through this exercise is that the difference between a manually tuned receiver and a spectrum analyzer, the spectrum analyzer does all the work for you. Otherwise, it's exactly the same thing. And in this case, we happen to be tuned to 156.7. There's no way that I can find a transmitter that might be operating at a different frequency. I can only look at this particular frequency. One of the things about a receiver is that it requires an antenna to receive something. In this particular case, I'm using a whip antenna, which is a little screw-on whip antenna. These are readily available from people that sell two-way radio supplies. But if I take the antenna off, we receive nothing. So you have to have an antenna to receive something. This is a directional antenna. It's the particular band it's designed to use for is about 450 megahertz. The lower the frequency, the larger the antenna becomes. When you're looking for direction finding, particularly when you're out in the field looking for a transmitter that may be in a number of houses or buried someplace, this is directional enough to give you an indication of what bearing it comes from. This particular antenna gets maximum signal pointed in the direction of the boom. So unfortunately, they get very large and cumbersome as you go to low frequencies. So if you're looking for something in about 100 megahertz buried in the FM band or below that, the antennas get unwieldy and they're very large and difficult to use. They look like a regular TV antenna. But again, you need an antenna, and this is a directional antenna. In most cases, it receives only in one direction, so if you're looking for something in a large area, you want a non-directional antenna, like the little whip that's on the back of the receiver. The automatic receiver is a spectrum analyzer. There's a wide range of spectrum analyzers ranging in quality and price, and as you might expect, the more expensive the analyzer, the more features, quality, resolution, precision that they have available. There's spectrum analyzers have been relatively widely produced now for over 20 years. There's a lot of them available used. A lot of the used ones don't have the precision of the new ones, but they're perfectly adequate for some purposes. I have here a Tektronix 2710. It has some neat features for our applications as well as many other ones. This one has digital storage and digital displays of everything, so it's very instructive of what's going on. It's easy to use, but it's not unique and it's not the only one you can use. Some of the lower cost ones are equally usable, but they're a little bit less precise. If you're looking for specific frequencies, a little bit harder to find out exactly where they are. The least cost ones do not have a digital display. They're not very accurate or precise. They're enough to tell you whether there's something there or not. And the utility is not that greatly diminished. You don't need precision attenuation and precision frequency readout for the kinds of applications we're talking about. Let's walk through the controls. I'll skip some of the ones. I'll say don't worry about these because this has a lot of features you don't really need to know about and you don't really have on all analyzers. We have a display, and in this particular display and on most spectrum analyzers, the horizontal scale is frequency. The vertical scale is amplitude, the strength of the signal. The display in this particular case is looking at from 0 to 1.8 gigahertz. So each division of the scale is 180 megahertz. We can change that. I'll show you how. The vertical display right now shows minus 30 dBm at the top, and then you see the broad band of noise here, or grass as it's commonly called. That's the noise floor of the instrument. You can't receive anything lower than that in this particular mode. This particular analyzer, because it's digitally controlled, uses a lot of buttons to do things. The older analog analyzers, everything was done with rotary knobs to select things. But we have in the center the frequency and marker knob, which will dial up whatever frequency that you want to put in the exact center of the display. We can change the frequency manually. I can also directly enter it from the keyboard, which is a lot faster. The frequency span per division here, those 4 keys control the horizontal scale of the display. In this particular mode I'm looking at is max span. If I take it out of max span, it thinks for a minute. And now we're looking at a display which is more conventional. It's showing amplitude and frequency. We're at 500 kilohertz per division, so that 162.4 is in the center. That's the weather transmitter we're listening to earlier. And then other things are 500 kilohertz in increments above and below that. I can change that by increasing or decreasing the span per division. And as I go to narrower spans per division, things spread apart. Also, because it's automatic, the trace also is slower. And note how the trace changes here. It's slowly sweeping through frequencies. So if something is coming and going, we miss it while it's sweeping, unless you happen to be lucky and catch it when it does that. Going in the other direction, we can put them closer together. So now we're looking at a lot of things. We're looking at 2 megahertz per division, so we're going from high 150s to almost 170 megahertz. The 4 RF level buttons control the vertical scale, and I can increase the display, except that you'll notice the noise floor moves up when I do that. I can decrease it. You see in the upper left corner the display changes, and it gets to the point where it doesn't see anything because it has no sensitivity. I've turned it down too far. Back to minus 30. The next 4 buttons below there have the resolution, which is how broad a bandwidth the receiver is that's sweeping through the frequencies. And there's a distinct trade-off between accuracy and resolution and speed. The more accurate your display, the more resolution power you have, the slower the display has to be to keep your accuracy. This particular device is automatic, so as you change things around, it'll follow you. You can force it to be manual, and when you do that, it warns you saying it's uncalibrated. And you notice in the 3 kilohertz bandwidth, the trace moves very slowly. If I manually force it to go faster, its calibration is suspect, and you may not see things that actually exist. I can go in the other direction and look for wider bandwidths. As you go in wider bandwidths, you'll notice that the noise floor dramatically increases, which means that things that are buried are lost. On this particular device, I turn on the detector, and we can listen to it as it sweeps. It's kind of hard to understand what's going on. One of the neat things this will do is that you can put in a very slow sweep, and you can hear a little bit of each thing as it goes by. Even at the slow scan, it's hard to quite make out what's going on. So there's a mode called zero span, which when you select that, it becomes a fixed tune receiver just like the manually tuned receiver. The other thing that's important to notice is that the bandwidth of the receiver, here shown as 30 kilohertz, is too narrow to modulate a wideband FM station. So we have to increase the bandwidth in order to make it intelligible. I'm going to show you some typical spectrum here. This is channel 20. I'm using some of the convenience features of the Tektronix analyzer here. It says right there UHF channel 20. Dead center is channel 20 visual carrier. You'll notice about 3.8 megahertz above that there's a little mark. That's the color subcarrier. So you can tell whether the station's in color or not. And 4.5 megahertz directly above that, right on the edge here, is the aural subcarrier. In the United States, every visual carrier will have an aural 4.5 megahertz above that. Every TV channel, with a couple of weird exceptions, is spaced 6 megahertz. So if you're looking at the whole TV band, you'll see them spaced every 6 megahertz. This is a portion of the FM broadcast band. You can see in the center is 98.9 megahertz. I've set the divisions to 800 kilohertz per division because most FM stations are spaced by 800 kilohertz. Makes it easier to note them. Let's kind of spread this apart a little bit now to see what an FM station looks like when you look at it very closely. You notice every time I switch that, the kilohertz per division over in this corner changes, and the image spreads apart. I've now dialed up a part of the VHF band around 152.5 megahertz. This band is useful for illustration that it's showing things that come and go. Some of the frequency carriers you see there are for mobile telephones, some of these for paging, some of these for other things. And what I'm going to do is I'm going to listen to a particular frequency which is located about here, and you'll see it come and go, and you'll hear it come up with all sorts of funny noises. That's digital paging. If you're watching real closely, it happened right there. And there's several other ones came and went while we were listening to that. What's important when you try to look for things is to have a good idea of what's going on in whatever band that you're looking at, because there's lots of stuff out there. Some of it is perfectly legitimate transmitters. Some of it may be spurious noise caused by computers or other electronic devices in your neighborhood. And some of that might be a little transmitter, which is what we're looking for. A very useful piece of advice, particularly for those who have never used an analyzer before, is to get your hands on one, take it home, and learn how to use the instrument and learn what is actually out there in the RF band. There are hundreds and sometimes thousands of legitimate transmissions going on in any given area. And you need to know which ones are legit, which ones are noise or something caused maybe by a computer in your neighborhood, and which ones just might be a transmitter which may or may not be interested in what you're looking for. And when you have situations like here, you've got carriers that come and go, it's hard to pick out what's really there and what isn't. And you almost have to dial through and listen to them and learn what they sound like, what paging sound like, what two-way radio sounds like, what various forms of digital transmission sounds like, what a TV signal looks and sounds like, what FM broadcast looks and sounds like, aircraft band, all kinds of things, because they can be buried all over the band. I'm going to kind of start here, just kind of give you an overview of looking for a transmitter. I'm really cheating because I know that there's a transmitter, but I'll show you how to kind of look for things. So the first thing that I would do is go to the widest sweep available in the analyzer, which, and here's by pressing one button. There's a lot of stuff when you look at the entire spectrum between 0 and 1.8 gigahertz. But if you kind of know where the FM band is, where the TV band is, where the two-way radio people are, stuff starts to show up and you know where it is. One of the things that's real obvious, if we reduce the sensitivity, is that most of those transmitters are relatively far away. So if you're in an area and you think you might be close to even a very low power transmitter, it'll show up. In the overall band, you notice lots of things are buried down at the low end. This is mostly the FM band. That's where the most strongest transmitters. Secondly, the TV transmitters, which are above and below the FM band. We can spread this out a little bit here. Just watch the display go through all of this little mode. This is so much fun. We're looking at here in the middle is the FM band. There's a lot of noise in this area, which is probably a computer or some kind of a thing. But if you have a good idea what it should look like, then you can find it. Let's go back to max span again. And mysteriously enough, some little transmitter will show up. All of a sudden, you notice over in this corner here at about 180 megahertz, there's something that's actually off screen. It's a very strong little transmitter. And it isn't always this dramatic and obvious. We're doing this here to make it easier to see. But there is a little dot right there above the 5 megahertz, and that's a transmitter. And even at this very low sensitivity, I'm seeing something there, and I'm seeing several harmonics of it show up. I'm going to make it look a little more obvious. There's one right at about 180, there's one right about 360, there's one right about at the third and fourth harmonic. Anytime you see something very strong and things integrally related to that, 9 chances out of 10 you're looking at a very simple, inexpensive, low-power transmitter. They don't have the harmonic attenuation that more sophisticated transmitters have. You make them small and compact, they tend to have lots of harmonics. It's real easy to see. Well, here's our little transmitter at 169. Let's dial up that frequency exactly and look in that vicinity of 169 megahertz. Take it out of max band, it works better. Now, we're using the internal detector on this. We might be able to actually, once we buy it, you won't hear it, so we'll stop. Go into zero span, and we get feedback, which will give away not only that there's a transmitter there, but it'll also give away that you found the transmitter. So it may be a good idea to listen with headphones while you're doing that, but that's relatively easy to find when something is that powerful and that obvious. I've set up a little demonstration here using a two-way radio service generator right here as a signal source rather than a little transmitter. It's more controllable and precise. And because it's not very sensitive, I put the mic right on top of the receiver so that we can get a little feedback to demonstrate when I actually find the frequency, it'll feed back. I know what the frequency is, but I'm not going to tell you what the frequency is. If we take a good look at this shot here, a good close-up of the screen, you'll see that there's a number of carriers there, and they're all kind of there. They're all at about the same amplitude. None of them are particularly strong. This is when it starts to get hard to find things, because ones that are well buried, and somebody who knows what he's doing will bury them well, make it harder to find. The first thing that you can eliminate is the ones that come and go. The carriers that come and go are probably paging or two-way radio or something. So if you stare at it long enough, you'll notice that, a couple of these are here all the time. And you can take a mental note of the frequencies, approximately, although I can do it smarter by using the marker here. We'll move the little red dot around. That one seems to be there all the time. It doesn't change. It's 152 of 52. The one below it seems to have stuff that comes and goes around it. Oop, that one just went away. Well, it can't be that one. All right, well, let's go back over, try this one here. What's going on at 152.24? That one stay put? It seems to stay put. Okay, well, let's check it out. Let's go to zero span. Turn off the marker. Zero span, dial 152.24. Let's find the carrier. There it is. And it just went away. Well, that's not it. Let's maybe dial through here. Maybe I'll be lucky and find it. That's a RCC telephone carrier. That's not it. What do we have here? 152.59. You can see it go up and down as I dial around it. 152.6 is where it seems to want to be. It's maximum. It's very quiet. Now, if I had a receiver, I could turn up the receiver here and get feedback. So we found it. And just kind of repeat this a little bit here. Go back to the display. The carriers that come and go we can forget. This one up here is the one I was actually originally going to look for, and I stumbled across the right one. The ones that come and go, the ones that have paging, the ones that have somebody talking on it, you can eliminate it as they go. The carriers that come and go, you can discount because that's a two-way radio kind of an application. It's paging or something else. Carriers that have a continuous tone on it, that have digital paging, other kinds of noises. So you can use the receiver or the spectrum analyzer in a manual mode to slowly dial through the band and listen to each one, if it has an internal detector. The ones without an internal detector, you're completely blind. You need a scanner or a receiver to find them. So you have to think about what you see and not just say, yep, spectrum analyzer gives me a picture of what's going on. that's it, I can find it on the first try. The harder to find small transmitters are the ones that will test your knowledge and skills and patience, because they invariably will be buried with a bunch of other things that would tend to obscure their existence. In summary, spectrum analyzers are like any other tool. In a trained and experienced hand, they're very useful. They're not hard to use. You should not be intimidated by them. You really can't hurt them by playing around with them. The only thing you can hurt them by is by connecting them directly to a transmitter, like a two-way radio, or I don't think you'd see a broadcast transmitter or a high-power paging transmitter. But if you just use an outside antenna, you can't hurt them. Play with it, learn how to use it. There are some things that they're real useful to find, and they can be used out of ranges that you wouldn't expect. For example, we're back here to the widespan. There's something buried in there that we're looking for. There's one other example of finding things. This happens to be something that is not in a band that is normally used by VHF kinds of devices, although it's very common. You can buy them easily. I can't tune it with the ICOM receiver, but it's there. So let's take it out of maximum span. We're going to notice something. There's a carrier here. It looks to be at 200 kilohertz per division. It's a little bit under halfway between those two divisions, so I would guess that it's 260, 270 kilohertz. It's not quite 300 kilohertz. So let's dial down there and see what we can find. Too far. When you start using the low end of the band, you're going to notice something interesting. The large spike right here is 0, and below that is an image. Ignore everything below the large spike. That's 0 frequency. Below that is negative frequency. Actually, this machine's smart to say that's negative frequency. But let's go back looking for this weird little spike here. I wonder what that's coming from. Well, we can dial it up here. I'm sneaking up on it. I can count it if I want to. The machine will count it automatically. It'll display it up in this corner. Has to think. It's 259.022 kilohertz. I wonder what that is. Well, put it in 0 span here, which turns this into a manual receiver. And I get feedback. What we're looking at is a little wireless room monitor made by a local neighborhood electronics supplier that you can buy anywhere. This receiver, the spectrum analyzer, can actually receive and demodulate that. The ICOM VHF receiver cannot. Most communications receivers that are designed for shortwave listening cannot receive FM at that lower frequency. So having a 10 kilohertz to 1.8 gigahertz precision tuned receiver can really make a difference.
Bye, guys. This is a look at some of the devices currently on the market for both bugging rooms and tapping telephones. As you can see by our selection, There are quite a few units available, and they vary greatly in their looks and their capacities. These are infinity transmitters. Although they go on the telephone, they're actually room bugs, allowing one to hear what's going on in the room from another telephone. This is an old-fashioned style that doesn't work on the new telephones. This one is a dedicated infinity transmitter. When you call up, the phone never rings, but rather transmits the sound. It needs a dedicated line all by itself. A number of other units on the market are set up so the telephone will ring one or more times, allowing the user a window of vulnerability in which to grab the line and listen to the room conversation. This little unit here goes in the telephone and does exactly this. It's also possible now to buy complete phones with infinity transmitters built in. This one from Listen Electronics, you dial, it rings once, and you have 12 seconds in which to dial back, and it will grab the line and let you hear room conversation. Very difficult units to find. These are telephone taps. They're designed to pick up and rebroadcast telephone conversations. Some of them have batteries for longer range but shorter life, but most of them attach directly across the telephone wire itself. This means they can stay active forever. This is a 3-wire bug. It gets room conversation as well as telephone conversation and rebroadcasts it. This is a modern 3-wire bug, does approximately the same thing. This teeny little unit is often hidden in the handset of the telephone itself. Very powerful little unit. This is a law enforcement model, works well too. These are room bugs. Most of them are powered by batteries, either externally or internally. They can be hidden any place in a room. They're very sensitive. They'll pick up conversation from quite a few feet away. This is simply a professional wireless mic. It's been left in the on position and can be placed anywhere in the room. This is a very powerful little unit, fully adjustable frequency. Who uses a typewriter? What an ideal place to put a bug. What a beautiful place to put a bug. It'll pick up everything said in this room and maybe the next one. This particular bug is very powerful, will broadcast at least 1,000 feet, if not more. And it sits in this typewriter until somebody takes it out. Pictures on the wall. Plants are a real special favorite of people that plant these things. No pun intended. Put the device in a plant. It sits on an executive's desk. We've even found people who will place a bug in an envelope, often a special delivery or express mail envelope, address it to somebody who they know is on vacation for a couple of weeks, write personal, confidential on it. Today's bugging units can be so flat, especially if you use a Polaroid camera battery that's a flat lithium battery, surface technology, it feels like a letter. Mail it to the guy, personal, confidential, secretary lays it on his desk. It sits there in a very hot area for who knows how long, broadcasts until the batteries run down. Something else to remember when we're talking about bugs is most bugs, especially those that work on a battery, have a limited lifespan. How long? Well, it depends on the bug, it depends on the power output, and it depends on the batteries involved. But it's generally safe to say that a bug will last anywhere from 1 to 3 days. Now this means that most people will not just go in, take a risk, plant a bug, and see what they get. It's not worth that. Most bugs are targeted for specific times. Is there a big conference meeting? Do we have a budget meeting? Do we have a bunch of executives getting together? That's when you want the bug in effect. And that's when you want to look for the bug. Not 2 days before because it may not be there, and not 2 days afterwards because it may not be there. Right before the meeting. Bear this in mind when you do a search. Now this is not universally true. The bug could be hooked up to the mains, the power that comes into the office, just be running forever. But if it's a battery-powered unit, it has a limited lifespan, or someone has to come in and change those batteries, taking a risk. So you need to do your physical search. You need to go through every piece of paper, every shelf, every filing cabinet, behind every picture on the wall, baseboards on the wall, looking for wires. we're going to show you in just a second, every suspicious wire must be run down to its source. That is a potential bug. The easiest, most practical way to bug someplace is simply to hide a miniature microphone in the room or in a small hole in the wall near the room. Run some wires out. This doesn't radiate RF, very difficult to find except by physical search. If you find some wires you can't explain, alarm wires, wires in a telephone cable, or just wires running someplace, you must trace them down to their source and make sure it's not a hardwired bug. Past that, we have the RF bugs, and we're going to look at those right now. Now, radio frequency bugs have been around for a long time, and they've changed over the years. They've gotten a lot more sophisticated. The early days, the idea was to put as much power as possible into an RF bug. Now, this is a walkie-talkie, a couple of watts. How far? Bugs and taps with fairly simple equipment. Simple to use, simple to get. It's either fairly low priced or it can be rented and used. We're going to go up through the steps, starting with the easiest, most primitive methods and working up to the more sophisticated ones. You can use all these. Neither one excludes the other. The first thing that's important is physical search. Now, I'm going to say this a number of times in this video, and it really is important. It's the number one most important thing of any technical counter surveillance measures group. All sorts of fancy electronic equipment, that's great. It's going to help you find stuff. What if the bug isn't in use anymore? What if the batteries run down? What if the bug's equipped with a switch? So if they hear you searching, they turn it off. This is not outrageous. This is used by the FBI. It's used by a lot of other people as well. They hear you start a search, they turn it off. No electronic device is going to find that. Physical search is first. Now, while you're planning out your countermeasures survey, you need to decide an important factor, and that is, do you mind if the people who are listening know you're searching? In most cases, this should be a yes, you do mind. Because if they hear you searching, if they hear certain telltale sounds, it will show they know you found the bug, it's useless to them, they're going to get in their car and drive away. If you find the bug by yourself without them knowing, you have an opportunity to plant all sorts of false information, feed your competitors or your spouse or whomever things that you want them to know that may or may not be true, or you can simply try and catch them by saying certain things and seeing who shows up, you know, that sort of thing. So we're going to look at both ends of that. But again, first we're going to start with physical search. Now, we're in sort of an office environment here. You start with everything available. Start from the top and work down. Particular attention should be paid to anything that has a battery in it or plugs into the wall, especially things that may have been given as gifts. Easiest way to get a bug into a place without committing a burglary, give it to the guy. Hey, here's a calculator from, you know, A&E Printing, where you do all your work. Congratulations. Calculator has a battery in it, could easily have a transmitter in it. They're built that way. The telephone has its own power, often used for bugging devices. We've shown, later part of the film, how to take the phone apart, look for these devices, some tests to do on them. Do it. But physical search first. Take it apart and look at it. Turn over anything on the desk, any funny looking little things. Where'd this come from? Does it have a transmitter in it? Very possibly. Find out where it came from. Do whatever you can. In some cases, if you want to go to the expense, you can actually x-ray stuff or you can fluoroscope stuff. But usually a physical search will find many things that are there. Here's a typewriter. It's plugged into the wall. What an ideal source. Open it up. Look around. There may be computers over here. Local area network. Will this transmit? Well, this is a powerful one. This will go 1 to 5 miles. Early bugs were designed with that in mind. Let's send the signal as far as we can. Let's, you know, make the people who are listening to the signal safe. Get them away. Not anymore. The idea now is to use the minimum amount of power required for several reasons. First of all, the batteries last a lot longer. A 1-watt walkie-talkie will eat batteries up in about 5 hours. A 50 milliwatt bug may go a day on a set of batteries. A 2 to 5 milliwatt bug lasts 18 hours, 2 days. Stack a couple batteries, you've got 4 days to a week on a bugging device. The ratio of range and battery power is not direct. There's a formula involved. Just adding more power does not make the range that much farther. A small 5 to 20 milliwatt bug will go 1,000 feet easily with the right receiver and the right conditions. Why do you need more than this? If you need more than this, you put a relay unit in a car, station it 500 feet away, picks up the signal, changes the frequency, rebroadcasts it to your receiver. So today's bugs are designed to be efficient on battery power and efficient on radiated power. This also makes them much harder to find. It's a fact that there are bugs out there, and there are people with scanners now and receivers that can pick up a lot of these frequencies. You put a real powerful bug in somebody's room, the chances of it being detected go up incredibly. A physical search means examining everything, looking in books, under books, behind pictures on the wall. Curtains are an ideal place for a bug. Lamps, behind calendars, any place. There may be a bug. You take the time, go through and look for something that doesn't belong there. Take apart the base of the lamp and look at it. See if there's a little black box in there. See if there's some circuitry that shouldn't be there. This is how you find a lot of bugs. If you had minimal access to a room, say you're in it for 30 seconds or 60 seconds, and you wanted to plant a bug, how would you do it? One of the best ways is go underneath, go under a cabinet, go under a shelf. A little bit of tape, 30 seconds, and you've planted a bug. Physical search has to include a telephone. First thing to do is to disassemble your phone and look for things that shouldn't be there. This is known as the strip search or the sneak and peek. You need to check out the button, make sure it looks okay, feels okay. You need to look behind it in the handset and make sure nothing is hanging on the wires or stuffed up inside the handset itself. See, built-in microphone. These two devices run off the AC power. This one clamps across an AC cord. This obviously is designed to go right inside a wall socket. It has a transmitter built directly into the back of it. It will operate continuously as long as it's left in place and there's power in the house. These are examples of what we're looking for. Notice these units, notice how small they are. We need to find them. These are telephone dropout recorders. They're designed to pick up the telephone conversation when the phone is lifted off the hook and start a tape recorder. Some modern recorders do this automatically, while others require the addition of these small units. They're attached directly to the telephone lines and don't hinder the conversation in any way. This is a miniature video camera and fiber optics. This combination, although it doesn't use any wire, can transmit video and sometimes audio several thousand feet. These devices are often hidden in false ceilings. They're also commercially available in clocks, smoke detectors, phony safes, and books. The two things we're going to look at now are bugs and taps. Now there's a difference. When I say bugs, I'm referring to something that reproduces room audio. Phones can be bugged. This phone can be rigged so it reproduces the room audio either down the wire or through the air to a monitor of some sort. Normally, bugs are in other environments. Taps reproduce phone conversation. That's all. A tap, strictly speaking, will not reproduce the conversation going on in the room. A bug will. Some devices are designed to do both. They'll pick up phone conversation and room conversation. These are known as three-wire bugs. They're usually in the phone or on the phone wire. What we're going to look at first is bugs, what you do about them. First thing you do is you assess your threat level. In other words, sit down and plan it out. Who wants you? Jealous spouse, you're suspicious of a business partner, something like that, that's one level of threat. And that level of threat we can cope with pretty well by following a few fairly simple things. We can eliminate that level of threat. On the other hand, if you think the DEA wants you, the FBI, somebody even higher up than that, you got problems. They're going to use real good stuff that's designed to be difficult to find because more and more people on the wrong side of the law are finding the means to hire people to ferret out bugs. So it's getting harder to do. Technology is still always a little bit ahead of counter technology. But for the most part, we're going to show how you can find both